Alright, in this video I'm going to be really quickly going through the solutions to linear algebra homework 3.4, which is going to be more example problems on linear transformations. So the first one is got a 3x4 matrix where f is the linear transformation defined by f of x equals m times x. We're going to start by giving the domain and codomain of f. So I'm going to start by pointing out, okay, M is a 3x4 matrix, and if you know what that means, then feel free to go ahead and just say what the domain and codomain are, or you can just see it from the matrix, what the vectors x are going to look like and what the outputs are going to look like. Great, good for you. Just go for it. But if you need some convincing, or you need to remember why this is working the way it does, just point out that M is a 3x4 matrix, and what we're going to do is we're going to multiply it by a vector. And that vector is going to be something by 1, but we know that that would have to be 4 by 1. And that's going to give us, some output vector f of x, and 3x4 multiplied by 4 by 1, that's going to give us a 3 by 1 back. Okay, so we would say that the domain is going to be all the inputs, that would be all of R4, and the codomain would be the outputs, which is going to be all of R3. And it's going to ask us to find all solutions to the equation f of x equals 0. Okay, so we're just going to set up a system, augment a matrix with zeros, row reduce, interpret our solution. Okay, so I'm going to start by maybe adding row 2 onto row 3. And then I might subtract 2 of row 3 away from row 2 and 4 of row 3 away from row 1. And then maybe also multiply the middle row by -1 while I'm at it. And then if I keep going, oh no, I don't actually need to keep going at all because I'm in reduced row echelon form there. Okay, so now I'm going to interpret my solution, but before I do that, I think it's really easy to get mixed up on this and kind of say the wrong thing here. So I'm going to remind you that, the solution that we're looking for is a 4-dimensional vector, not a 3-dimensional vector. So, and that's because, like we're trying to solve the equation mx equals 0, and x is an element of R4 because that is the domain of our function. But also because, if I'm interpreting my answer down there, I've got 4 columns, that's 4 possible variables to my solution. So I'm going to go ahead and kind of interpret what the matrix is telling me and say, okay, 1x1 minus 6x4 equals 0, so that would be x1 equaling 6 of x4. Then x2 would equal -3 of x4, x3 would equal -2 of x4, and x4 can be whatever it wants, right? Only 3 pivots in a 4-column matrix. Okay, that means the homogeneous system has to have 1 free variable. Okay, we learned that a few times ago. Okay, and then from here, I think I'm ready to write down my answer and interpret my solution. I'm going to say, okay, the solution is the set of all vectors that can be written as the form 6 times a number, -3 times a number, -2 times a number, and that number in the 4th component. All right, number 2 is g of x is the linear transformation defined by g of x equals mx, and m is a 3x3 matrix in this case, so it's going to take in 3-dimensional vectors and give back 3-dimensional vectors. Okay, we're going to first find the value of g of a. Okay, so g of a, it says that's m times a, and so m times a would be 1 of the first column of m plus 1 of the second column of m minus 1 of the third column of m, and that's going to give me the 0 vector back. And then for part B, if we're trying to find all solutions to the equation g of x equals a, we're going to set up an augmented matrix, row reduce, and interpret our solution. So we're going to set up m augmented with a if we want mx equals a, and we're going to row reduce. So I'm going to say, all right, I kind of just first start by setting it up, and I'm going to probably subtract the 3rd row minus the 1st row, and leave everything else the same. And then I might add the 2nd row down onto the 3rd row and realize, and you might even look at this matrix right here and realize, okay, this system is not going to have a solution. But if I take it all the way to reduced row echelon form, it would look like that, and I can see, okay, I've got 0 equaling 1. This is going to be a no solution scenario. Okay, so there are no solutions to the equation g of x equals a. And if v of b is like the inverse function for g, or is the inverse, explain why v is not a linear transformation. I think there's probably a variety of explanations that would work for this, and I think you should try to think of one on your own. But one that I'll give you right now is that it's not a function. Okay, we just found that there was a non-zero vector. In part A, we found that g of a was 0. So we found that there was a non-zero vector that we could multiply m by to get the 0 vector back. And we've seen already, recently, that if there's one of these non-zero solutions, there's going to be infinitely many. So if I'm going backwards on the 0 vector, I'm going to be pulling back infinitely many solutions, essentially, because that's what the inverse does. It's like kind of an equation solver. So for part C, I'm going to say, all right, well, v of 0 is the set of all solutions to g of x equals 0. And, we already found one, so we know there's infinitely many. But on the other hand, the reduced row echelon form of M has 2 pivots and 3 columns. Right? We can see that kind of like right there to the left of the vertical bar in part B. It's got 2 pivots but 3 columns. That means that the homogeneous system mx equals 0 is going to have one free variable in its solution space. And one free variable, that does mean infinitely many solutions. And so that just means that v can't be a function, right? So because v of 0 would have multiple output values. Now for the next two, we're going to turn it around and not give you the standard matrix and kind of make that the point of the problem. Let's recover the standard matrix given just a couple of pieces of data about the transform. So suppose H is the transform from R2 to R2 defined by H of x equals AX, where A is not explicitly given, but we have these two values, f of 1 and 8 equals 2 and 2, and f of 3 and 25 equals 0 and 1. So we're going to start by finding the standard matrix for H. And I think I'm going to just, show you where we were in the lesson in class. And I showed you for 2x2 matrices, we can actually solve this one with matrix algebra. And it's really not too bad, especially when matrices or numbers are well chosen, which they're going to be in this class, right? So if we could write a matrix equation, AX equals B with these two pieces of data, we could use matrix algebra to rewrite A as B times X inverse on the right. And so I'm going to do that. I'm going to say start with x, and those are kind of our input vectors. So x is going to be 1, 8, and 3, 25. We're just going to package those into a matrix. And then b is going to be our outputs. So b would be 2, 2, and 0, 1. And we'll package that up into a matrix. We are going to need to find x inverse, and I don't really care how you do that, but you're going to need to find the inverse matrix, and you would need to arrive at that. But because part B has us finding the inverse of a 2x2 matrix, I'm not going to give all the details of x inverse. I'm just going to give the details on finding an inverse down there. But you know how to do that. We've been doing that for the entire course. So now what we need to do is to multiply b times x inverse on the right, and so I'm going to set up for that. A equals b times x inverse. And again, we're going to do that matrix multiplication, and you're going to do it however you do it. It doesn't really matter. We just need to arrive at this result. Okay, and that's part A. Now part B is we're going to find the inverse of the standard matrix for H. So we've got A equaling this 50, 42, -6, -5 matrix. So I'm going to need to find the inverse, and I'm going to start by taking the determinant of that matrix. So I'm going to say that the determinant of A is going to be 50 times -5 is -250, plus 6 times 42 would be 252. And I'm going to see that, okay, that determinant is 2. And if I want to take the inverse, I'm going to, divide by 2, because we need to divide by the determinant for a 2x2. And then we're going to swap the upper left and lower right, and we're going to make the other two negative. So that would be -42 and +6. We'll distribute the half, and we'll get the inverse matrix that we were asked to find. All right, now the last one I've got is a 3x3 case where we're going to solve this one with row reduction, okay, because we learned that technique also. So we've got 3 pieces of data for our 3x3 matrix that we don't know. We're going to find the standard matrix for T. And how we're going to do that is we're going to lay out the data as rows, do row operations on them, on these pieces of data, because that's just linear combinations, until we can figure out what is the output that corresponds to I, J, and K, because those will be the columns of our standard matrix. So I'm going to start with, part A. I'm going to start by saying, f of 1, 2, 4 equals 7, 4, -1. So I'm going to put 1, 2, 4 as a row and say that goes with 7, 4, -1. f of negative 1, 3, 0 is going to be equal to 2, 0, and negative 4, and f of negative 2, 1, and negative 1 equals negative 2, negative 1, negative 3. Okay. And now we're just going to start row reducing. So I'm going to add row 1 to row 2 and add 2 of row 1 to row 3. This is a matrix that we have reduced before in our class, in various other lessons. Maybe it looks familiar. You see that those 5s that are complementary. So I brought this one back out because I thought hopefully it would be familiar. And you can see how it would really work out nicely with this matrix here on the right. So we're going to start with that step, and then I'm going to subtract row 3 minus row 2 to take advantage of those 5s right there. And then, oh look, I've got a bunch of 3s in my bottom row, and so I'm probably going to divide that all by 3. And you can't really see that, but there you go. I'm going to divide that third row by 3, but then I'm also going to subtract 4 of that new row from rows 2 and 1. Okay, and so I'm getting closer. Now I'm going to look and see, oh, look at all those 5s. I can divide by 5. And then I'm going to have that, and I might subtract 2 copies of row 2 away from row 1 to get kind of my finished reduced row echelon form here, which is going to be the identity on the left and a transpose on the right, but I don't like that way of thinking about this technique. I like thinking about it as like, oh, hey, on the left-hand side, I've got these vectors, and then on the right-hand side, I've got their outputs. And the way linear transforms work, if I just do linear combinations of these vectors and their outputs, they'll stay, inputs and respective outputs. So I've got, I in the first row, J in the second row, K in the third row of the matrix on the left. And then I'm going to have the outputs corresponding to those vectors in the rows on the right. So A is going to be that landing spot for I, which is going to be 1, 0, 1. And then the landing spot for J, which is 1, 0, negative 1. And then the landing spot for K, which was 1, 1, 0. And there I've got my matrix, my standard matrix for the transform T. Okay, and then the last part, we're going to find the inverse of this matrix. And really, you can do this however you want. If you want to augment this A with the identity matrix and row reduce, that's a totally valid technique. If you want to go back and reverse the 2 matrices that we had up here at the top of A, you could do that. But I would not recommend doing that. That doesn't look like the most fun row reduction to me. You could use a calculator if you just had enough with the set of example problems. But for me, I'm just going to try to look at it and solve it. Thinking about it the way we did with elimination matrices, a couple weeks ago, because this matrix looks like it's all 1s and 0s and it's got a negative 1. I feel like I can do it. So I'm going to go in and I'm going to go for it. And I was able to do it earlier, so but I've got it. I'm just kind of going the tape on this, this writing. So hopefully I can remember how it went. Okay, so I'm just going to say, all right, I'm going to go for A inverse. And I know it's going to be a 3 by 3 because A is a 3 by 3. And so really my first row of A inverse, I need to think, how could I get the first row of the identity matrix from the rows of A? Okay, and I see that the kind of the elimination that's possible with that 1 and the negative 1 in the middle component. So I'm going to think about adding the first row to the third row. And if I did that, I'd have 2, 0, 1. Okay, and then I would need to subtract the middle row. I need to subtract the middle row. So I'm thinking I'm going to, I'm going to first multiply the first row by 1/2. Then I'm going to basically add the third row. Okay, so that's where you'd see the positive 1/2 in the right. Then subtract away those, 1s, and then divide everything by 2. Okay, and so you're going to see a lot of halves in this. Okay, so to get the middle row of the identity matrix, I think I'd need to subtract the first and third rows. So it's going to be half of the first row minus the second row to get rid of the number in the third column, plus minus half of the third row. So positive half, negative half, negative half. And then the last row of the identity matrix, I can see it. It's right there in the middle. So I'm just going to call for that by saying, okay, none of the first row, 1 of the second row, none of the third row. Yeah, go. And that's going to be my inverse matrix right there. All right, so there you go. So that's going to be all for this one, because I think, yep, that's all the problems we've got. So thanks for watching.